I'm Oscar Tavares. I'm the co-investigator for the NSF grant that we have right down here at the Alpena Community College, the World Center for Concrete Technology. This program and this grant involves the use of carbon dioxide as a sustainability in concrete block and concrete products. The history that we have right now from other researchers is that most researchers have had to use pressure above the normal ambient pressure that we have in concrete manufacturing, above 1 atmosphere pressure, and elevated temperatures above normal ambient temperatures. And all the research has been done in a laboratory environment. What's unique about our program is that we actually manufacture our concrete block here and place it into a chamber. What we also did was we manufactured our own curing chamber, which allows us to monitor the humidity, the temperature, the weight of the block, the absorption of the carbon dioxide onto the block. We will do this at no pressure, at elevated temperatures, as the heat from the heat of hydration of the block is being manufactured by the cement hydration. Also, in reference to testing of what we have done, we have already proven the previous research that has been done in this sustainability of carbon dioxide into concrete products by proving that pressure does work at a pressure of 100 psi of CO2 pressure and less than that. But they always have to apply something greater than 20 psi of pressure. We in our studies don't believe that pressure is necessary because a normal block producer in a block plant will not be able to pressurize his system or her system. Also, the present data that we have presently is that we're trying to reduce from using 100% CO2 down to 50% CO2, down to 25% CO2. And the purpose of this is that if we are able to sequester carbon dioxide from manufacturing plants that use energy and we can recapture that CO2 from this energy, we will be able to sustainability reduce the total CO2 impact, not only on the atmosphere, but also to utilize the CO2 in concrete products. Now, the purpose of this research grant is how can it be applied to normal product applications. We're doing the studies basically on concrete block units, which have to pass ASTM C90 at such compressive strengths and at such water absorption and shrinkage. So this testing that we're doing today will prove that all the blocks up to date have passed the requirements of C90. On compressive strengths, you have to meet the minimum strength of 1900 psi. The water absorption has to be less than 25%, and the shrinkage has to be less than whatever the control is. So up to date, all of our tests that we have done today has proven that the strengths up through 28 days meets the normal requirements of C190. Now, the other thing that we're trying to do is optimize the system where a concrete block manufacturing producer can get all these 3 parameters in less than 24 hours. So therefore, the carbon dioxide, the purpose of the carbon dioxide is to accelerate the system that we have in the chamber, but also to accelerate the system for a block manufacturer in a plant. So the purpose of what we're doing right now is trying to cut the energy cost, trying to sustainably use carbon dioxide, and to manufacture the same type of quality of block or better block. Also, in reference to this grant, what we're trying to do, we're trying to use this information that we gather to have a teaching moment for students here at the college, but also so that we can go forward and teach high school students in the community if they have interest in being involved in a technology position at a local block producer or ready-mix supplier. So that's the other purpose of this NSF program, is that it's a teaching moment besides trying to get data that's real life use information for a block producer.
My name is Kate Richards Bruski, and I am a co-PI on the Alpena Community College NSF project with Oscar Tavares and Don McMaster, and I'm also responsible for outreach to K-12 and the community in general, providing information about this project. And we do that in a variety of ways. We initially met with 9 area schools and talked to them about the project, told them a little bit of detail about it, and also about what we might like to do in working with them. Primarily, we were looking at STEM classes, science, technology, engineering, and math. And the feedback that we got from the 9 schools was that the curricular demands of those very rigid classes were, and budget. We live in a wide geographical area. Many of our schools are pretty far away from ACC. So budget and curricular demands were really compromising our ability to work with them and their ability to visit us and work with us. So we had to go back and think really hard about that. And we came up with some ideas, and we have primarily been working with building trades classes who have much more flexible curricula and are able to, their budgets are just as stringent, unfortunately, but we are working with schools that are a little bit closer in proximity to us so that we can provide them transportation to visit us if necessary, and we have done a couple of times. And we're also doing a lot online. We're taking advantage of the web to provide information, so there is no budget issue, and the instructors are able to utilize the information that we put out there for them as they are able. On the web, we've built a National Science Foundation website through our Alpena Community College web. It's a daughter page, a child page, and it provides all kinds of information, just a wealth of information about concrete technology, about sustainability, about building trades, all kinds of lesson plans that instructors may use if they have the time, articles and sources about all of those topics. And we found that some of them are being engaged, so that's really exciting. And to reach students a little better, we built a Facebook page, so that's becoming increasingly popular. And we put the same sorts of things that we have made available on the NSF website on the Facebook page. We just think we have a little bit different market there. So then part of a significant part of this outreach is to provide job fairs, trade shows, and sustainability fairs, information about all of those topics I mentioned: sustainability, concrete technology, research into what we're doing on this project in carbon sequestration and concrete curing. So we engage those building trades classes because their schedules are so much more flexible. And we've worked with 3 schools that are a little bit closer to us and provided them transportation so that they could bring their classes here. And we gave them tours of the Concrete Techs, the World Center for Concrete, and we provided talks from a variety of presenters at 2 different job fairs, one in 2012 and one in 2013. The most recent thing we've done in terms of outreach was go to the state capitol and meet with Michigan Department of Education administrators and talk to them about using the online curricula that we have developed for at the World Center for Concrete in providing to dual enrolled high school students statewide, or perhaps even farther, certification in concrete technology. This would give them college credit while they're still in high school. So that's very exciting.
We determined that in order to accomplish the goals of this project, we had to purchase a chamber that was big enough to handle 9 8x8x16 concrete blocks. In addition to that, it had to be able to handle pressure up to 20 psi and also vacuum. In addition to that, we had to be able to monitor the relative humidity inside the chamber. We also had to monitor the temperature inside the chamber and the weight of the block while it was in the chamber. In searching for a chamber of the correct size, we found out that the cost of a chamber that would do these capabilities was over $20,000. At that point in time, we took a look at what we could do to make a chamber ourselves. And so we designed a chamber and had it built for the specifications that we determined. We designed a chamber made out of stainless steel plate, 10 gauge, and had it reinforced with 2-inch channel iron because of the pressure that's of 22 psi that's going to be submitted to the chamber itself. We also added a heating element inside so we can control the temperature. We added 2 flow controls, one for air and one for CO2 that we'll be introducing during the trials. We also added a humidistat inside for checking the humidity and a temperature gauge so that we could monitor the temperature also. We also added a safety release valve to protect ourselves from overpressuring the tank, and we added a vacuum port so that we could suck the air out or the CO2 out depending on what part of the project we were trialing at that time. The chamber sets on a pallet scale that's calibrated down to 1/100th of a pound, and that sits on a metal frame supporting the entire unit. The cost of the chamber that we had built came to $4,500, and the scale itself was $650. So it was a considerable savings building it ourselves versus going out and buying one commercially.
I'm Eric Krebs. I'm the former director of the World Center for Concrete Technology up in Alpena, Michigan. And I'm one of the team members on the sequestration of CO2 in concrete masonry. This is a National Science Foundation grant that has been secured by Alpena Community College and the World Center for Concrete Technology. My job in this effort has been to design the mix designs for the blending of the aggregates that are being tested. Of course, those aggregates to us are normal MDOT standards here in Michigan, but 2NS sand has been provided to us. That's our fine aggregate, and then we have a coarse aggregate, a 29A. Those two have been proportioned in 70% sand and 30% stone. We have added also a 1:11 cement to aggregate ratio. That means 1 part cement to 11 parts aggregate. So now those are all mixed up together in a typical ribbon style mixer. That takes approximately 4 to 6 minutes. Then it's conveyed to the block machine. That's a unique feature of the World Center for Concrete Technology. We have a full concrete masonry plant here. In this particular case, we were using 4-inch masonry units that were run approximately 6 at a time, and we would make about 9 or 10 pallets, wanting to make sure those were acceptable in dimension characteristics. Then we would convey those over to the chamber, get them in the chamber, and then others in the project would take off and start the CO2 ingestion into the chamber, control the relative humidity of the chamber and the temperature of the chamber. So my main objective was to control the consistency of the product. And of course, if we can control that, we can control the density of the product also. The density will directly affect how far the CO2 will penetrate into the product. By densities, I mean typically that's going to be in a concrete block is about 130 pounds per cubic foot density. Think about a paving stone. Now that's a lot more dense, and that's going to be at about 140 pounds per cubic foot density. So we think if we can keep track of that density and those levels, then we will probably have that consistency in the research that we've developed and the findings that we'll secure.
I'm Don McMaster, Dean of Workforce Development at Alpena Community College. I'm the Director of the World Center for Concrete Technology, and I'm the Principal Investigator on the NSF ATE grant. The World Center of Concrete Technology at Alpena Community College is a public-private partnership that's unique in the concrete industry worldwide. And it represents a niche that Alpena Community College has in concrete technology training, industry testing, and workforce development. The NSF ATE grants sprang from that, and it represents an awareness we have that concrete is the second most widely used commodity in the world outside of fresh water. And if you were to stand anywhere in the world and turn 360 degrees, you would probably see concrete. So in terms of sustainability and an international worldwide imprint, our project, which is investigating the sequestration of CO2 in concrete masonry product, has significance. Alpena Community College had never applied for an NSF grant before. We'd never had one in 60 years. Most community colleges are unaware that NSF has a program called the Advanced Technical Education Track that allows for funding to support research that's done at community college campuses. That research tends to be more of an applications orientation, in line with the students we see, 2-year hands-on associate degree, applied education. I want to commend the NSF folks and the American Association of Community Colleges for making this track available for community colleges. It really resonates with students that we see. A lot of them go out and have great careers in a hands-on orientation, not heavily geared toward research, and our project has fit in and aligned with that very well.